Hi guys, in this video we're going to finally introduce the simple linear regression model. And so simple linear regression sometimes is abbreviated SLR. It also goes by other terms such as least squares regression, the least squares regression line. Okay, so you'll see this word least squares come up a lot, and you'll see why hopefully by the end of this video. But essentially, linear regression, let's get a couple definitions out of the way, and there's going to be a little bit of terminology before we get to the actual model and technique. Okay, so linear regression, it can be defined in many ways, but essentially it's fitting a line to bivariate numerical data. So we've already talked about, let me just squeeze data in here. So we've already talked about bivariate numerical data, things like a house's price and the square footage, age, height, number of years of experience, income. All those are examples. That was 3 examples of bivariate data sets. Okay, so what we did first was we made a scatter plot. We calculated the correlation coefficient. Obviously, we analyzed the scatter plot. Now we want to fit a line to that scatter plot. Okay, so let's get some more terms out of the way, and we'll kind of, I'll give you some visuals on this. So in regression analysis, we want to use information. So let me say use info. About an independent variable x to predict values of a dependent variable y. So if you recall, up to this point in this series, it didn't matter which variable in the bivariate numerical data set you called x and which you called y. It didn't matter when you were creating the scatter plot. It didn't matter when you calculated the correlation coefficient. Here, it starts to matter. Okay? The x variable, so the variable that we will call x, okay, rather, will be the independent variable. So let's, and it goes by a couple of synonyms, so it will be independent. It also goes by explanatory. It also goes by predictor. And there are even more. Okay, so let's limit it to these 3. The y variable will be the dependent. The response, sometimes also called the outcome variable. So these are terms you should become familiar with, familiarize yourself with. In the meantime, let's look at some of those, one of those scatter plots that we saw earlier. And basically what we're asking here is, does the scatter plot exhibit any kind of linear pattern? So if we recall, we talked about this, and we annotated this with this data set over here. So we had this data, which was concerning how much a house sold for and how big was the house as far as how many square feet did it have. So we just willy-nilly chose to call house price y and square feet x without any real purpose, and that was fine at that stage. That was an exploratory stage. We didn't really know what we were after. We didn't have a clear objective yet. Okay, and then we made a scatter plot. Try to ignore all the writing on it. Just look at the blue points. If you recall, and we actually have this info here, we came to some interesting insights. We saw that there was a positive relationship between how many square feet a house has and how much it sold for. So there's a positive, kind of moderate to strong, linear relationship between the square footage of a house and the price it sells for. So if we were to actually see a scatter plot that exhibited a linear pattern like this, we might want to take a step further than just saying these things and maybe calculating the correlation coefficient, which we should also do here. We didn't complete this, but this is quite strong, so something in the neighborhood of 0.86. Let me just ask you to agree with that as a good guess. At some point we'll see what it actually is for this data. But there's something I want to do a little further than just these points that I've learned. Okay, I want to be able to summarize this relationship between the square footage and the house price with a line. So I already had this intuition to draw this line, right? And this is kind of came from my gut, if you remember. And if you drew the line to kind of summarize this relationship, you would have drawn something very similar to that line that I've drawn over there. Just slightly steeper, slightly less steep, slightly shifted up, slightly shifted down, but we would all come up with generally that same summary for the pattern. But I'm kind of done with the intuitive stage, and I want to move on to something more concrete. I want to be able to summarize this relationship between these two variables, this x and y, with a line that gets as close as possible to the points on the plot. Okay, so not just a line from my gut, from my intuition, which is definitely a start, but a line that actually comes as close as possible to all the points on the plot. Okay, that's what I'm after. All right, so to understand this, we have to understand a little bit more about a line. So let me do a quick review of lines. So remember the equation of a line, you might have learned it as y equals mx plus b. Now m was the y-intercept. That's where the line crosses the y-axis. So if this is x and this is y and this is our line, this is the y-intercept, okay? And b is the slope. So you've definitely seen this in your algebra course at some point in your mathematical life, okay? The slope here in this particular example, we can at least say is negative something, right? And the intercept is whatever this value for y is, right? So what we're going to do is we're going to slightly alter this form, and we're going to say y equals b0 plus b1x, and you'll see that I've just replaced m and b with b0 and b1. b0 rather, let's do that first, is our y-intercept. I just realized I made a huge mistake here, right? In this previous equation, and if you caught that, well, God bless you. M was actually our slope here, right? And B was our y-intercept, okay? So if you caught that, God bless you. In our line down here, B0 is our y-intercept. The one that's connected to the x variable is our slope. So, okay, so B1 is my slope, okay? And on top of that, I'm going to add a little hat to y. And a hat in statistics means estimate or predicted. So that if I put a hat on y, I'm saying that's an estimate of y. That's a prediction of y. As opposed to if I take the hat off, that's actually what y is. So that will be clear why we need that in a second. But let's get a little more terminology out of the way. B0 and B1 collectively are going to be called our regression. coefficients. Okay, so collectively they're called the regression coefficients. And B0 is the y-intercept, which I misspelled, and B1 is the slope. And remember that a slope, whether you call it B1 or M, like you probably used to, is just rise over run. If you have a negative slope, it's fall over run. If you have a positive slope, it's rise over run, right? And the y-intercept we kind of explained already is the point where the line crosses the y-axis. So that'll be our review so far for line, and now you just have slightly new notation and a little new vocabulary here. So just get used to this form over the old form that you've used. All right, so now let's go to a scatter plot and actually see this in action. Okay, so I have a nice clean scatter plot of this same data that we had here. Before I show it to you, let's make clear why I put the square footage here and the house price on the y-axis. Up to now, I just asked you to accept that, and it didn't really matter which variable I called x and which I called y. Now I will give you some extra information. This problem, if I were to have given you some background, this is a real estate broker's attempt to come up with better listing prices for properties they're selling in their area. This data that we're looking at, this bivariate numerical data here, are houses that have already been sold. So we know obviously how big the house was and how much it sold for. So what the broker is trying to do is to see if there is a relationship between how big a house is and how much it sells for. And if there is, to be able to summarize that relationship and use that information to make predictions of how much a new house that hasn't been sold yet, but we know how big it is, how much that house is going to sell for. Okay, so again, they're trying to predict how much a house is going to sell for based on how big the house is in square footage. So knowing that, we call house price our y variable and square footage our x. Y is what we want to predict. X is the predictor. They go by different names, but one of the names of x is the predictor variable, the independent variable, the explanatory. It explains y, it predicts y, and it is independent. Y, however, is dependent on x, so it's called the dependent variable. It responds to x, so we call it the response variable. It is an outcome, a result, if you will, so we call it sometimes the outcome variable. So having given you that background about what our objective was, or what the broker's objective was, you can then decide which variable is y and which is x. So it very much matters in regression which variable you call y and which you call x. Once you've decided that, everything else you do will depend on which variable you called y and which you called x. We made this scatter plot using putting house price on the y-axis and square footage on the x. Okay, so we'll go forward now and look at this scatter plot a little larger and see how simple linear regression and least squares regression works. So here are the same set of points on a slightly bigger chart, and here's just the line. I'm asking you to accept that line for now as the B0 plus B1x has the best fit line. Okay, so I'm going to give you the line and then work backwards to show you how we came up with that line. So this line looks very similar to the line that I drew just from my intuition up here. Just slightly different, okay? This is the best fit line, whereas this one was my best intuition, okay? This is the line that gets as close as possible to these points Okay? So what does that mean? So each one of these, so obviously you see that that there is no line that you could have drawn that would have touched all the points, or else you would have ended up with a curve, a very complicated curve that would be focusing on the noise rather than the pattern. So since we're confined to a line, the best thing we can do is to get as close as possible to all the points. So I'm going to draw little brackets from each of these points to this line. Okay? These brackets are just emphasizing the vertical distance between each of the points and the line. So this particular one is below the line, so this has a negative distance. This one has a positive distance. And if I draw one of these for all of these points, because they all matter, some of them are very close, some of them are further. Okay? We call this distance that I've got now, remember, n was 10 here. I have 10 points, so I'm going to have 10 of these brackets. Each one of these brackets represents the height from the point to the line, and we call that a residual. Okay? And we use the letter E to indicate the residuals. So there's going to be 10 residuals. So we're going to have, if I put a little I there, just fill in the blank 1 to 10 for I. And you're talking about a specific one. So here we have maybe E1, no specific order, E3, E5, E7, etc., etc. Okay, up to E10. So these are called the residuals, and there's going to be 10 of them. Now I want a line that gets as close as possible to all these points. It turns out that if I were to just focus on one of these, I can get the height of this actual bracket. So let's just focus on maybe this one because there's a lot of space around it. So let me draw a vertical line from the line down to the x value here, and that's a bit thick. Let's just draw it by hand. So I'm going to go up till I hit this point, and then I'm going to go over, straight of course, till I hit the y-axis. Okay, and this value here is y. That's the actual value for that point. If I continued up higher, I would hit the line, and then I would go over. This is the predicted value for this particular x that we went up on. So we call that y hat. So there's a difference between y and y hat. Y hat is what the line predicts or estimates y is at a particular x value. Y is what the value actually is at a particular x value. So since we focused on this guy, we might actually be able to see which observation this came from. So this is a little less than 2,500 square feet. So we could find that apartment, hopefully. Actually, it's the biggest apartment, right? Or house, rather. 2,450. It seems like we're talking about this guy here, right? 2,450, and the house sold for 324,000. So if I were to erase this and write the actual value, 2,450, we went up. Obviously this point was 2,450, comma 324. Remember x, y, that's how you plot points, right? So this particular point here is 2,450, 324. That means the height here is going to be 324, right? And if we continue to go up and go over to the line, this is not the actual amount that this house sold for. That's the predicted amount that a house of this size will sell for. Okay? So the difference between y hat and y seems to be the size of this bracket. So I can get E1 by doing y minus y hat. Right? That will give me the height of this bracket here. So I can get any one of the particular residuals by subtracting the predicted value from the actual value of y. Okay, so I can just generalize this now and say I can get EI by doing yi minus y hat I. Okay, so now I will tell you that we don't want to just focus on one of these points. We want a line that gets as close as possible to all of these points. So I need to look at them collectively. So I don't want just to get one point. I want to sum all of them. So I sum from 1 to n. N is 10 here, so I could fill in that blank, that value for 10. I want to sum all the points, so I would be able to do the same by summing the differences of the y's and the y hat i's. Now, I'll tell you, if you were to actually sum all these residuals, you will always end up with a big fat 0, and that gives you nothing to work with. So we square them, we square each one of them so that the negatives don't counteract the positives, and we actually have something to work with. And the points below the line are going to give us negative residuals. The points above the line are going to give us positive residuals. If you sum them up, they will give us 0. We square them to get rid of the negative sign. And so we're talking about the sum of the squared residuals here. And this has a name, RSS, and that stands for residual sum of squares. Residual sum of squares. Now, our objective to get this best fit line, this line that fits the points as close as possible, best fits them, is to minimize RSS. That minimizes RSS, minimizes this quantity, in other words, gets as close as possible to the points. And so we want a line, and we have the line written over here. We want a line that gets as close as possible to these points, in other words, minimizes RSS. And how do we define a line? B0 and B1 are what define a line. So we want the values for B0 and B1, the regression coefficients, such that we minimize RSS, this guy over here. Okay? So the least squares line, aka the sample regression line, is the line that minimizes this sum, the RSS. Okay? So I'm going to leave it to part 2 to actually go further with this. I think this one's gone on long enough.